We've all seen the classic architectural blueprint: clean lines, perfect angles, frozen in time. But that static image has very little to do with the dynamic reality of a modern, data-driven city. For decades, planning education has relied heavily on project-based learning. In this traditional model, an instructor hands a student a predefined design brief, and the student's entire job is to produce a fixed spatial artifact to match it, like a physical model or a map. The core limitation here is what the method assumes. It assumes the problem is already perfectly understood and safely bounded. The student doesn't have to define the problem, they only have to synthesize a design to solve it. Real urban environments don't work like that. Cities are what scientists call complex adaptive systems. They are messy, nonlinear, highly volatile networks that actively resist simple analytical reduction. We train future planners by having them execute static, prepackaged projects. They arrive in the real world completely unequipped to recognize, let alone frame, the highly ambiguous problems actually plaguing our streets. This gap in education has driven the rise of urban informatics, an emerging discipline that forces computer science, geographic information systems, and urban science to irreducibly integrate. To teach a discipline this complex, you have to abandon the practice of creating standalone design artifacts. You have to build a pedagogy based on constructing deep, iterative understanding. This flowchart illustrates the deep divide between the two educational logics. On the left, traditional project-based learning uses a divergent logic, starting with a brief and ending with an artifact. On the right, problem-based learning relies on a convergent logic, observing a phenomenon, inquiring, modeling, and extracting insight. Problem-based learning strips away the pre-packaged design brief. It drops students directly into an ambiguous, ill-structured phenomenon, say a neighborhood experiencing a sudden spike in transit delays, and offers no immediate instructions. By intentionally withholding the parameters, the method forces students to define exactly what they know and exactly what data they need to discover before they are allowed to attempt a solution. If the city itself is an unpredictable, ill-structured problem, the pedagogy used to understand it has to mirror that reality. It has to start with unstructured inquiry. To guide this inquiry, urban informatics relies on a specific 5-step cognitive framework: describe, inquire, model, extract, and state. In the describe and inquire steps, students observe a real urban phenomenon. Instead of accepting a written prompt, they have to physically and digitally observe the environment to identify the hidden causal mechanisms at play. Next is the model step. Students construct computational simulations mapping urban growth. These models aren't graded as final products. They are active tools of investigation. This requires a massive shift in mindset. In traditional project-based studios, a failed model is a bad grade. In problem-based learning, a failed model is highly valuable data. That data feeds directly into the extract step, where students analyze their multiple modeling iterations to identify clear patterns and generalizable insights. Finally, in this state step, they articulate evidence-based planning propositions. Every design choice they present must trace directly back to the data they extracted. Through this 5-step cycle, students learn to treat uncertainty as an epistemic resource, a mine of information to be explored, rather than a design flaw to be carefully hidden. To successfully execute this framework, the core power dynamic of the classroom has to shift. In the traditional model, the instructor acts as a design critic, broadcasting subjective judgment on a final product. But in problem-based learning, the instructor is repositioned as a Socratic facilitator. The facilitator uses their expertise to diagnose superficial inquiry. When a student hits a wall, the instructor doesn't deliver the answer. They force the student to ask a better question. By removing the instructor as the sole source of truth, students are forced to rely entirely on rigorous, evidence-based argumentation to defend their choices. We are currently building a global urban future that is sensor-rich, algorithm-driven, and intensely complicated. The professionals tasked with managing these environments cannot be passive recipients. Out in the field, there is no predefined brief handed down by a professor. Navigating this complexity requires deeply ingrained scientific habits, relentless observation, hypothesis formation, and evidence-based assertion. Mastering the modern city requires the capacity to stand in the face of immense, unstructured complexity and continually ask the right questions.